you have this. Okay, so let's just maybe try to present your poster and guide audience in the logical way, and we all will try our best to record some comments and provide feedback for improvement.
There we go.
Hello, Sarah. Nice seeing you connected.
Hi, Dr. Killian. Hi, everybody.
So this is the poster I did at Visitation Day, which I'm using as a basis for the Sanibel poster. But the major thing, so the one major issue with this compared to the Sanibel is I only have my single layer models, which I don't remember how we finally decided to phrase them. I have to remember how we decided to phrase them in the end, where I need to include my heterostructure model, so my double perovskite layer models, so with multiple perovskite layers. So I have, right now what I have is I have my models up top here. I have density of states, which I'll probably need to reduce and maybe remake, because I'm thinking that I'm probably not going to be able to fit 4 pictures for density of states. And we have some photoluminescence that I did for this. But I don't have the multi-layer model here, like I mentioned earlier. And we're definitely going to want that, because the major focus on the poster that I'm doing is comparing the single layer to the multi-layer. As for the red field tensor and the occupation, I basically included them on this poster to try and include a good overview of what we do as a group, because this was for Visitation Day. If I could fit them, they'd be nice, but I don't know if I realistically could fit those on here. For the relaxation, I need to pick and choose which ones give the best outcome for what we're trying to do, which means which is probably going to be the n=4 model, and then the 1/4 model. As for this little table I have here, I think it goes over well what I'm doing, but I don't know how I could realistically present it once I get in my multi-layer models. Yeah. Any comments would be appreciated at this point.
Okay, please join me in thanking David for being the pioneer of the year. So, and any questions are very welcome. Please feel free to type in the chat line, or just speak out loud right away.
What exactly is your poster about?
So I am looking at the optical electric properties of 2-dimensional lead halide perovskites. And in the process of this, I am comparing single layer models. So if we look at my model right here, can you see my mouse? So if you look at these, these are what I am terming as single layer models because there's only a single perovskite layer. I also have ones where there are two perovskite layers of different thicknesses. So the idea is that we're comparing these single layer ones to the multi-layer ones to see if there is an additive effect or if there's a completely different effect or.
I guess one thing that I would ask then is, what did you find out?
It appears that well, I'm hearing feedback now. It appears that there is not an additive effect. Okay. It appears to be relatively unrelated to the multi-layers appear to be relatively unrelated to their single layer. With the exception of the ones that involve n equals 3 and an odd total number of layers, so like 2 and 3 or 3 and 4 seem to have some of the characteristics of n equals 3 single layer for some reason. And I have not figured out why.
Well, and did David satisfy your curiosity, or you want more?
I do want a little bit more. I'm also trying not to have a feedback loop between all of us in the office, though. So I guess what are the ends representing in like the n equals 1? Because I guess I had assumed that was the
so if you
like
look
how many layers.
That is what it is. So if you look at it, the brown atom is lead. So how many leads there are is indicative of the n. So in the one I'm pointing at, there's two, so that's n equals 2. Here there's 3. Yeah. So what I have pictured here is n1 equals 1 through n equals 4. In my heterostructure model, which do I have something that I could bring that up quick? What's this one? No, that's not it.
Your heterostructure being the one with like different thicknesses of layers. So you had mentioned something about that.
Documents, group meeting presentations, 1920. That's the one I want. How do I stop sharing the screen or share a different screen?
Well, I have one comment to make to mention.
Yeah, talk while I try and figure this out.
The density of states that you have, since they all appear to be on the same scale, you could slightly compact it.
That is one of my plans, is to try and compact them. I don't see how to stop sharing screen.
Should just be the same button, right?
Is someone smarter than me?
Is this one that you're on?
So I'm on this one. I'm trying to get to this one.
Oh, where's your menu thing?
where's
Yeah,
your
you should have
control
like move your mouse like down to the bottom or something, like hover it.
Oh, I found it.
Oh, I see. You got a monitors. Oh, okay.
I'll just send 2 more people. Travel screen, lanes, teleport to the internet.
So if you look at this page, this is what I mean by heterostructure or multi-layered model. So you see that I have an n equals 1 layer, then on top of it, there's an n equals 4 layer.
Okay.
And I have others for that.
What were the other molecules that you got going on here? They look like carbon chains or something.
So there is a propyl diammoniums. Those are the organic linkers. So the way my model works is it is a perovskite layer separated by an organic layer. And what the organic layer does is creates a hydrophobic region that the perovskite, so the perovskite forms a film when you have periodic boundaries.
Okay.
I'm so excited that instead of looking at improving the poster, I have the scientific question. So it's for the future work, not for the poster.
Yep.
In your hybrid models, you are stacking multi-layer models on the top of each other, right?
Yep.
Do you have in your repository, or maybe you are planning to do models when instead of being stacked, they are placed side by side?
So the next step that I'm doing, and I am currently in the process of I'm currently optimizing. Most of these is one that's already optimized, and I'm in the next process for it. Models where I have these multi-layers where they're side by side with the hope that they'll funnel electrons.
Exactly. Perfect. Yeah, that's great. That's great.
So the hope would be that they'll funnel electrons and holes to opposite ends, creating charge separation.
Yeah, super. And I see London is nodding to approve this idea as well. Okay.
And I think I've been using my hand gestures at the wrong screen as I'm looking at this.
So, David, if no one is against, maybe let's return back to the poster and check if there are more questions. So, any questions from Haley would be of the top value, because
if you look at the top right, Landon, you can see the atoms.
So Haley, even if something is not clear or new, just declare it, because the merit of a speaker is to deliver material for broad audience, and you will point out what is not self-explanatory.
Okay, I don't know what any of these diagrams mean.
Like, if I would see it for the first time, I would ask something like, what's the difference between green and blue diagrams? But maybe you'll ask something different.
I mean, what diagram do you want to look at?
What's the density of states?
Density of states. So that is the indication of where the electronic configuration is. So there is a state at approximately -1 on this one, and we've broadened it with a Gaussian.
There's no labels on here. On the
EV, it's at the bottom.
There's on the very bottom.
So and we've broadened the peak with a Gaussian approximation. So the higher the energy is, the higher the peak, the more states that are there. The purple shaded region is occupied, the unshaded region is unoccupied.
Haley, do you approve the answer? It satisfies your curiosity to an extent?
Yeah, sorry, I thought you could hear me. That makes a little bit of sense.
Okay, yeah, thank you.
There are other figures you wanted to look at?
What's this?
So that's the occupancy of the one you're specifically looking at is the occupancy of the hole. So we initially excited this to HOMO -3, and as it goes down, so this axis is time. So as time, it relaxes down initially to HOMO -2 and HOMO -3, which are degenerate. And then it further relaxes into HOMO -1 and HOMO, which are again degenerate. So because I'm doing spin orbit coupling, every orbital has a degeneracy. And then the other one is the same thing, except for the electron. It was initially excited to LUMO +6, and it then relaxes toward the band edge with time. This was for the n=4 model.
So there is a question from you recently typed.
Where? Chat. There's chat. Is there a trend of relaxation rates for different layers? Not that I've noticed. They all seem to relax fairly similarly. The major difference, if we go down here, is we tend to see a peak, a partial relaxation before, so it goes to a slightly lower excited state before going to the band edge, and we see that in basically all of the models that I've looked at, and we see the same thing with the whole relaxation.
Is your question satisfied, or was there is a continuation?
Seems there's a distortion for the n=1, maybe not stable. Every single one of my models has this. I'm assuming this is what you're looking at for the what you're saying is the distortion.
Yes.
Every single one of the models shows that. It's just because the n=1 is zoomed in, it's much easier to see. So you can see the same thing right there in the n=2 and right here in the n=3. Like I've rerun that multiple times because I initially thought the same thing as you, but every time it's giving me that.
Is it possible to just characterize the local environment, like the bound angle, or?
I should be able to, but I have not done that.
To add to this discussion, three-dimensional perovskites take three crystallographic forms: cubic, orthorhombic, and tetra something. Oh, hello, Aaron. Nice seeing you connected. Probably Aaron remembers this at most. So what are the three phases, crystallographic phases of perovskites? Like cubic, orthorhombic, and something, the third, tetra.
Not gonal, but it's tetra something.
Okay, good enough. And if one explores, I don't know about two-dimensional, but for three-dimensional perovskites, if one explores them at absolute zero, the most energetically stable configuration, crystallographic phase, is not cubic. So some distortions are expected. And maybe if David would explore average shape at room temperature or like elevated temperatures, then it will be more stable. But these distortions do not look as a big surprise. And it looks like in the alternating layers, this like distortions are in the opposite direction. So they, in average, compensate each other to keep the volume.
I have another question. So I guess in the density of states, you have shown some orbitals.
Yeah.
So is this just the homolumal orbitals?
Yeah, those are just homolumal.
So it's really hard to say. So does the localization always the same? for different
So
models?
with the exception of the N=3, the HOMOs on the chlorine, the LUMOs on the lead. For the N=3, they're both on the lead.
So N=3 is a bad guy.
Yeah. And we were explaining this as it's the s orbital on the lead takes preference in the N=3 for some reason.
Okay.
Do you have any data for a higher number of layers or just to 4?
I have, well, I have optimized through N=6, but I have not done molecular dynamics for anything beyond N=4.
Okay.
Other questions from, well, anyone is welcome, but maybe Kea and Sarah want to ask something, because there are some connections between methodology and style of results of what David is showing and what you are going to show in shortly. Kea, do you have any critical comments to David's poster?
I saw when you shared his poster and others' poster in by email, I saw his poster looks good. It's
Okay.
perfect.
Okay, yeah, thank you.
It's the overall looks good, and obviously he knows everything about that, so no issues.
Thank you. Sarah, do you want to criticize David's poster, or maybe glorify in a style similar to Kea?
Yeah, the poster looks good. I just have a question, and it is that what is the difference between radiative and non-radiative relaxation calculation? Actually, this is Pishy's question. Maluz.
So the
Very cute.
non-radiative relaxation would be your phonon interactions, where the radiative would be radiative relaxation. So the non-radiative is primarily coming off as heat and is intraband, where our radiative, we see the initial excitation for this is basically right where this top peak is. That's like 2.7 eV. I'd have to look up the number to be positive again. I think it's this one right here. I'd have to look it up. And then this one right here is the band gap. So what we're looking at is this one is relaxing to the band edge. This one is from the band gap, relaxing across the band gap is the primary way to consider that. There is some outside of that, like this peak right here is probably an interband relaxation yet. And it matches about this distance. For the N=4, the cell is expanded in the y-axis as well. Yes.
Why you decide to expand in y-axis as well?
No, y-axis, no. Which one am I thinking of?
I'm trying, let me try to reformulate the question of Yulun. Do you actually compute results for n equals 4 by expanding your simulation cell in both z and y direction, or all models have the same size in y direction, but you expand it a little bit more only for visualization?
Yes.
Okay, so it is just visualization to look it more beautiful. But if it is the case, you can enclose the unit cell in a box just on a poster.
Yeah, I can do that. Z-axis. What do you mean by z-axis, Stephen?
What I meant is just sort of assuming that we're looking on the XY plane. It's for
so z-axis. We're looking at the XZ plane.
Okay. The XZ plane. Well, in that case, I meant y-axis. But the front to back axis is what I was referring to. In regards to Dr. Hahn's question of whether it's expanded as a unit cell. So it's, if we were to flip the n equals 4 sideways, it would still only be
Yeah, it'd be two cells thick. All of them are 2 cells thick. Okay. At David, for n equals 4, do you want to increase the font size of blue sock? Yes, I can do that.
Thank you.
David, can you go back to the right field tensor?
Yeah.
Yep.
I was going to say that.
What's the difference between these two?
So the right one is a log scale, the left one is not. So I made this poster for Visitation Day. So I was just trying to show how they work. So this one, because you can't see all these peaks, I made it so you could see them. And I made it primarily because it was for Visitation Day.
Okay, because I saw you were comparing 2 different models.
No, that's the exact same model, except the one on the right is log scale.
Okay.
For the red field tensor, correct me if I'm wrong. Why do I not see the LUMO? I only see HOMO on both sides.
Because I did not label the LUMO. I labeled the HOMO, and the LUMO is the one next to it.
The LUMO is the one next to it.
So right here would be LUMO.
Oh,
And then HOMO's right next to it.
oh, okay.
So when I labeled the axis, I labeled HOMO, figuring that you could figure out where LUMO was because it's the one next to HOMO. So I only labeled HOMO minus 10, HOMO minus 5, HOMO, LUMO plus 5, and LUMO plus 10 when I did it. It was just to make it less cluttered.
Yeah, thank you, David. Thank you, Lolo, for the question. Aaron, do you have any criticism or comments or questions?
I don't know, from the corner of the poster I've seen, I don't really have any questions.
So you are requesting that zoom out to see the whole poster.
Well, I guess while I'm here. So I guess for your non-radiative figure, like is like where the time axis cuts off, is that the end of the simulation?
I don't remember why I cut it off there.
Because it seems like it's still.
I think
Yeah, it
that was
seems-
where it stabilized, but I could probably run it farther. I do not have the modification you were working on where it eventually cuts out.
Mhm. Yeah, it looks, well, based on the black line, it looks like it barely almost reaches like full occupation in the LUMO. So it might be worth just extending the x-axis out to like 100 picoseconds or a nanosecond,
Okay.
just to make it look like you're not trying to hide something. That's always the easiest question to ask.
And maybe the natural answer would be like nothing essential happens after this time point, therefore we exclude it from demonstration.
The computational details, one can delete, align those black borders around the deck boxes. Probably.
Thank you. I do have a couple of questions, but they're not smart. They're more organizational. So suppose you are presenting in front of unbiased audience. What would be the order? Like if you focusing attention of audience, what would be the order of presentation? Like from which figure to which you want the attention to follow?
So I was thinking left, right column from top to bottom. But this table makes no sense in that order.
But can you just verbalize the logic? For example, like from methods to results, or from simple to complicated, or from structure to properties, like just general. What is the take-home message of a random visitor who visits your poster for 1 minute?
So we're moving from the methods into our structure, into more details on the structure, into our results with our photoluminescence, or not photo absorption. There is some luminescence there. Then we're moving into our relaxation, which is the more complicated. And I'm not entirely sure what I'm going to put here yet.
Well, hypothetically, one can convert this table into graphical format, but it's up to you. It's like you may have better vision. Maybe make 4 tables for each model, or make it like rates as function of energy as a dots on a. But it's your creativity. Another, I have a couple more questions. Which labels do you plan to add to some figures? Like, do you have any plan to label any features, or what would be?
So it depends on how much I need to condense these.
Mm-hmm.
If they were to stay here, I'd like to add figure labels to the DOS that could correspond to our absorption.
Mm-hmm.
But it really depends on whether I can leave this many DOS separated like this, or if I have to condense them down.
Mm-hmm.
And we could do the same general idea with this, the non-radiative figure and our radiative figure. So I could relate this back to this gap, whatever the gap ends up being from band edge, or this one could be, actually I'm pointing at the wrong figure, but from here to here, whatever it is.
Okay, so not as like researcher in this area, but just aesthetically as a visitor of random poster, I think the blue figure looks very lonely without labels. So there are many features, but it's not clear what it is.
I can tend to agree with that.
Maybe it could be first priority for labeling. Another question, what would you like to brag about the methods you used? So like, even if you didn't develop any of the methods, maybe they are like novel enough, state of the art, and you want to just brag that you use something cool. What like, again, if a visitor visits your poster for a minute and doesn't have special interest, what as a take-home message, what are the key points?
The spinor cone sham orbitals.
Okay, anything else?
I don't know.
So let me ask you to move your mouse to the central column, lower region. Yes, this one. So this is photoluminescence, right?
Yeah, so that'd be this one.
And why this one is worse or better than the one in your rightmost blue figure? Like how to compare?
So this one takes into account the trajectory of the molecule.
And let's point, may I ask you to point rightmost spikes near blue figure to the right? Yes. So what's the width, what the line width of this emission lines? Not a number, just how would you characterize it? Like, is it something that you compute or something that you set as a parameter?
Parameter?
Yes, so by operating software, you tell, okay, let my line width will be 0.1 EV, and then all of your lines have the same line width, right? Mm-hmm. So let's return back to the previous figure. Yes, what is the line width here?
It's related to the intensity of the photoluminescence intensity.
And if you redo everything at like 77 Kelvin or 500 Kelvin, would you get the same profiles or would they differ?
They would differ.
How would the width change with increase of temperature?
They'd get wider.
Okay, and it would be reasonable to brag about it. So by it is a natural way to predict line width. It's not parameters that you set up. You compute ab initio prediction for the line width, and eventually one can compare this with experimental results.
Okay.
And, okay. Whew. Any more questions to David? Questions 1? Questions 2?
I have a question. Oh, sorry. Can you mute? Sorry. Actually, that was a question of Dr. Kirino in Aaron Doctor of Defense. I'm not sure whether I didn't get the question or didn't get the answer of the Aaron. So that was about the absorption spectrum. So if we plot the absorption versus transition energy, each peak, for instance, tell us how much energy is needed to, for instance, a pair of electrons be promoted from one orbital to another orbital. So it's kind of about excitation energy. So then Dr. Kirino, I think, asked if it's about the transition energy. So it's kind of related to dynamic properties of the charge carriers. How did you calculate that by ground state calculations? So is that the question, or I don't know. I was mistaken in some way. So David, do you have any idea on that, or others? I don't know, Dr. Killian.
David, would you like to try, or Aaron had some?
I have no idea.
Well, Amir, you mentioned a question of my defense. I think I remember, like, I think one of my labels for my figures was excited state absorption, and Dr. Kalina took issue with that statement because technically all absorptions is an excited state property. So I guess the main idea is that, like, we call things, a lot of the things that we call excited states, we use the ground states geometries and ground state trajectories, which is an approximation, but is a valid one for a lot of the materials that we work with, because they don't change a lot, like in the excited state. Is that kind of the question you were asking?
I think so. So I didn't get the last part of your answer. You said the geometry in the excited state is not that different by the grounded state structure.
For some materials, like if you're dealing with like silicon or something that's very covalently bonded,
So
like in the
how can
excited state.
Then if just true for some part of materials, how we can trust the absorption spectrum results from the grounded state calculation for a library of the materials? For instance, for conjugated polymer, how can I understand if it's true or it's truly, actually the value is truly reported or no? Did you get
Well, I mean, the
question?
true answer is always experiment. So that's kind of where you have to figure out if it compares well to experiment or not. Because everything we do is an approximation. It's just how good of an approximation it is.
Okay, so if we do not have the experimental value for some new materials, what's the benefit of take advantage of the, I don't know, or utilization of the DFT calculations?
You sound like a critical reviewer.
Amir just is learning possible answers to a critical reviewer to use it, to add them to his arsenal. When someone asks him, he will know what to answer. So let me add to discussion. The absorption, in some sense, I agree with Aaron that absorption deals with property of a material in a ground state, because before photon comes to the material, it is in a ground state, and during the instantaneous interaction with photon, there are no much changes. So it's quite trustable. I wouldn't emphasize the word DFT. There are much more precise methods, but general electronic structure calculations for absorption are reasonable. And even if they're not super precise, they give a good prompt in which range of spectrum one may expect properties if the material is novel. Now, the corrections to optical properties. So if we are looking not on absorption, but on the emission, the spectra would be much more sensitive to material changes upon photoexcitation. And one can identify at least 3 factors that would play a role for emission of a material. So first, interaction of electron and hole, so formation of a bound state. When excited electron and excited hole attract each other, and due to this effect, the band gap energy efficiently gets smaller. Second, that upon photoexcitation, the interatomic distances rearrange, and typically it also leads to the fact that band gap becomes smaller than in the absorption. And the third factor is that if one is doing experiment or trying to simulate the experiment for material at ambient temperature, not absolute zero, then there is an inhomogeneous broadening. Since all interatomic bonds experience motion, and as they get closer or further away from each other, potential edge surfaces come closer or further from each other. So there is a distribution of possible transition energies, like an ensemble. And different methods address or ignore some of these effects in calculations. If you do have rigid crystal with then these effects are less pronounced. If you have small molecule or soft molecule made of organics, then all three effects will be much pronounced. So for the model that you're working at, all three are important. For crystals that David is working at, it is a little, all three corrections a little less important, but here David addressed at least one of them, how the spectrum changes due to average over ensemble, or due to thermal motion of ions. Did it satisfy your curiosity?
Yeah,
Okay.
thank you.
Thank you. And if anyone identifies errors in what I've told, please feel free to speak up. Okay, more questions to David. More questions one. More questions two. More questions three. Let's thank David once again. So David, please consider to implement changes as you see them reasonable. And Sarah, would you like to share screen and show your poster?
Hi, Dr. Green. Yes, I can share with you and get the audience comments regarding that. But for its presentation, maybe next week, because I need
do not consider it seriously. It's very informal.
Oh, really?
Well, on the conference it will be more formal, but here everyone is like friends, so it's just a chance to provide some feedback. And I believe I made you co-host, so you should be able to share a screen.
Yes, just because I need to download this one. Let me download it soon. Yes, as all of you know, what I did in this work, actually we studied the behavior of the Mons marlinite. It's one type of the clay mineral, using the density functional theory to understand the electrical and structural properties of these minerals, also the photoluminescence and some non-adiabatic calculation. So as you can see in the left, this is the introduction part. It explains about what is the clay and this type of clay mineral and the structure, its application in several industries. And then in the last part, I explained that which properties we measured or calculated using the density functional theory. And then for the method parts, I just, because of lack of space, I just mentioned several equations. You can see the equation for the quotient in the top, and you can see the the equation for the absorption spectra, and also the equation for the electron dynamics and photoluminescence in the bottom. And for the results and discussion part, because I didn't have enough space, I just delete the partial density of the state. I just kept the density of the states plot. And here I have a question about the figures. If everything looks good, or should I delete some of them, or should I keep all of them, or anything else, adding some explanation about them, or no? So this is a question from you, and after giving my presentation, you can discuss it with me, and I really appreciate that. And for the result part, you can see in the top the plots of the density of states for different spin multiplicities, low, middle, or intermediate, and high spin multiplicities. I showed the band gap on each figure, and you can see that for the alpha spin, for example, I have much larger band gap in comparison with the low with the beta spin. And for the second, I don't know why this happened. These symbols, I don't know why it doesn't show. It shows like a question mark, but actually they are not a question mark. Something like bullet. But and for the second part, it is a non-adiabatic calculation, and actually because of the again lack of space, I just explained one sentence that is in the following. You can see the charge carrier as a function of energy and space, and also the relaxation dynamic plots and the absorption spectra for different spin multiplicities in order. It shows in the top there, and these results are the for low spin multiplicity, and the second one corresponds to the middle, and the third one or the last one is corresponds to the high spin multiplicity. And also I mentioned that they are interpreted in terms of the alpha and the beta spins. Top row corresponds to the alpha, and the bottom row corresponds to the beta. This is also valid for other plots. And then I will explain that, for example, for each spin multiplicities, you can see that actually it seems that the electron or the electron is going to relax. The whole actually the whole relaxes faster than the electrons for the low and the intermediate spin multiplicities. And then I explained regarding this emission and excitation plots. Actually, I need to just refresh the results one time more, because I don't have enough. Maybe I mostly forget some part of it. But you can see that these peaks, actually the peaks with the highest intensity corresponds to the HOMO to LUMO transition, and for most of the cases. And actually, we can also mention the position of the electrons and the holes for the unit cell. For example, the holes are first on the oxygen in the aluminum octahedral sheet, then they will concentrate on the iron, for example. And again, this is valid for most of the cases. For the high spin multiplicity, actually, for the beta component, we took a look at several transitions, which again shows all of them has the highest intensity occurred in the HOMO to LUMO transition. And overall, for the conclusion part, I mentioned the most important findings that we found. I just explained that for the first one, the fundamental electronic, optical, photoluminescence properties of this type of material, montmorillonite, Fe, iron doped montmorillonite, were studied using the DFT based computational approach. Then I started mentioning the results. The density of state, actually the ground state results show that for the density of a state, the band gap of the spin majority or the alpha spin compounds is greater than the spin, the beta spin in all three cases. And then I mentioned about the charge carrier dynamics results, which shows the hole relaxes faster than the electron, just for the low and intermediate spin multiplicities. Then the results of the dynamics of excitation energy, it shows that the explicit transition corresponds to the HOMO to LUMO, as I said before, in the case of the low and the middle spin multiplicities. And as you can see from the figures, for the high spin multiplicities, in the case of the alpha component, there isn't any transition below the 4.6 electron volt, and in this figure you can see just until the 3.2 electron volts. And finally, we can say that we investigated for dominant transition for the beta component, and for the highest spin multiplicity, that we can see the HOMO to LUMO again has the highest orbital transition energy in all four in all these four transition, actually. Yeah. And at the end, I didn't know how to write the acknowledgement part. I just mentioned the support from the NDSU and NERSC for the computation. Yeah.
Okay. Yeah. Thank you much. Please join me in thanking Sarah.
Thank you. Sorry, I know that it was so awful, but
no, it is great. It is great. It's a lot of results and interesting story. So the paper is open for discussion. Any feedback, words of admiration, or constructive comments are very welcome. Haley, do you have any areas where you want to focus our attention and tell that something is mostly unclear, or something that you feel you want to learn more and maybe have relation to your own project? Like, what catches your eye?
So the blue plots are like emission spectra, right?
The blue plot, you mean this one, the purple one?
Is that what that is?
Yeah, these plots are actually the relaxation dynamics plots. For example, in the left, you can see this is the emission spectra, and panel B corresponds to the excitation one. Yeah. So what's your question?
What does that mean?
What does that mean? Okay. These spectra actually, the emission and the excitation, it means that the amount of energy or the photon that's the material absorbed, and it reflected back after the absorption. I think so. And each of these intensities correspond to one transition, one special transition. For example, if I'm not wrong, for this case, it is, for example, LUMO minus 17 to HOMO plus something, or here you can share, for example, LUMO plus 2 to HOMO minus 17 to LUMO plus 2, for example. These plots are actually, they are related to each other. The top one are the charge carrier as a function of the energy, and the panel B corresponds to the charge carrier as a function of the space. So these plots are related to each other. Yeah, it shows that this difference. I think the amount of the energy that the material just absorbed and reflected back. Yeah, if I'm not wrong. What do you think, Dr. Klein?
Yeah, makes sense. Makes sense. So those figures, which to my eyes they are blue, but you call them purple, which maybe okay. They are intermediate data to generate photoluminescence spectra.
Mm-hmm.
Okay, good. Haley, does it make sense? Does it satisfy your curiosity?
More sense than it did before.
Okay, thank you. Any questions from Lola?
None. I don't have any question.
Okay. Any comments or questions from Kea? I really liked last time, instead of giving critical questions, she just told how nice the presentation was. So maybe, Kea, would you like to say something good about this poster?
I have no comments, but Sarah said that acknowledgement part, maybe she can add like, I don't know what she wrote in her acknowledgement part. Maybe if suppose NER is that one, or ND Sparso, if those are related, like that acknowledgement section, it means that which one, what kind of things you used, like suppose you have the funding from professor, that one also the acknowledgement part.
Yeah, you mean mentioning the grant number, for example.
Yeah, yes.
Yeah, because I'm not sure what to write here. I just left it blank. So I'm looking forward to hear Dr. Klein's comments regarding that.
And you can also ask Professor Shah for if some of his grants need to be acknowledged.
Yeah, good.
Maybe you can mention CCAST if you were using it.
No, we didn't use CCAS for this result here. Actually, all of them were by photon or the NERSC.
Okay. Thank
So,
you.
So what about your grants? Do you have any?
I'll give some suggestions.
Okay. Okay, thank you. So what is your comments regarding the shape of the poster? Is there any suggestion to improve it?
Yes, but I do not want to move attention of everyone away from current shape. Let's collect. I'll share later on, but maybe there are some other comments or questions.
Yeah, okay, great, thank you. So in the chat, David first asked me, no, Amir first asked me, introduction and conclusions are pretty large, a lot text. Yeah, I agree with the introduction part, but conclusion, I think it's okay, but the introduction, yeah, it is too long, yeah. Maybe we can save some space here by reducing the length of the introduction. Thanks. And then David said, what do you mean by low spin, middle spin, and high spin multiplicities? I mean, n of the unequal to 1, n of the unequal to 3, and n of the unequal to 5 by this one. Yeah, I mean the difference between the alpha and the beta component, yeah.
David, does it make sense, the answer?
It makes sense to me, but it makes sense entirely because I've heard you give presentation on this before.
Okay, would it be, again, it's up to Sarah, but would it be reasonable to maybe add diagram of d-level splitting and populate them with arrows up and down to show these three configurations? Like,
I think that would make a lot more sense, and I would probably get rid of the word multiplicity as well.
You mean, Dr. Killen, the diagram related to crystal field, something you shared with me for the...
Yes, David, would you like to draw maybe on a piece of paper and show it in the screen?
برام راحت تره تو گوشیم همیشه دستم.
So I did high spin and low spin here.
Okay.
And, even it looks simple, but it would help to those visitors who are not sure if they want to devote their time to the poster, and they just pass by within 30 seconds, and if they recognize this diagram, they will be attracted and look further.
Okay. Yeah, I see. Thank you. Yeah, I tried to add it to the poster as well.
Just a quick note on your setup, you have a lot of white space, especially around the green figs.
Yes, I just didn't want to change the aspect ratio of the figure. Yeah, yeah, you're right. Thanks.
One thing that you might be able to do is organize it into like 4 columns, and where you have the 2 figures side by side, you could squish that into 1 column, and then where you have 3 or 4 figures wide, you might be able to span that across 2 of the columns, and that might wind up giving you a little bit better, I guess, packing fraction than your poster.
Yep, good suggestion. Thanks.
Steven, do you have any expression of admiration or critical, how to say, constructive suggestions?
No, everything that I can think of the ask a question about was covered pretty thoroughly by the others already. The only thing I am a little bit confused about actually would be how the what I see in the methods section relates exactly to the figures. There were a few of those on the other previous posters, but there's a lot more of them on this one, and I'm not entirely sure sort of how they can like relate. But that might just be a me thing that I need to look at it longer.
Yeah, thank you, Stephen. So what is missing, or what should be added, or which terms? What would you add, or what do you see missing? Like, can you explain your suggestion in more details? Like, let me tell as I interpret suggestion of Stephen. The ideal equations should roll one from another. Like next equation uses a symbol from previous equation, and then they are in a chain logically. And Stephen suggests that maybe the chain is broken and some symbols are skipped and not explained. Stephen, do I interpret you correctly?
Yeah, that sounds about what I was going for. Just a little confused exactly of sort of how the equations you're using relate exactly to the figures that you're showing.
Okay.
I think I get what it's supposed to be, but I'm not certain. I wouldn't feel confident saying, "Oh, this is what I think this is saying."
So,
considering,
David, please go ahead.
And considering there's such a big part of your poster, I don't see the equation for the green figures anywhere. I mean, I could be missing it. I'm looking at the equations are pretty small where I'm looking, but I don't see the equation for the green figs, and I'm not seeing the equation for the DOS either.
Okay. Yeah. Yeah, I just have the photoluminescence equations and just a small formula for imposing the initial condition for the thermostat.
So it's all understandable that one squeezes a lot of information in a limited space, and some things are skipped. But if they're skipped, they may need to be explained by words.
Yep.
So, Sarah, may I ask you to navigate your cursor, your marker towards equations block?
Yes, sure.
Okay. Down to the yes, and yeah, about here, next line for photoluminescence. So the F in the after summation, we have F for here F for oscillator strengths. Then
Yes.
delta depends on transition energy. This is also clear. And then next in the curly brackets, you have rho JJ sigma minus rho II sigma. So this symbol rho is not defined anywhere in your block of equations. So would you just share a vision what is rho and how it has been calculated? Just approximately, not without formulas, just basically what it is and how it corresponds to what you're showing.
Okay, sure. I will add the formula for this row as well.
Can you try telling it right now?
So it should be something related to the density, yeah?
Yes, density matrix. And I would you agree that those rho JJ and rho II are populations of orbitals, like how many electrons are on the orbitals, right?
Yes, for example, the II corresponds to the diagonal part of the matrix, yeah? And the IJ corresponds to the rest of the components.
But here you're using diagonal here and there, so you are just looking for population difference between two orbitals, right?
Yes.
orbital I and orbital J.
Mhm.
And if higher orbital has more population than lower orbital, they will emit. There will be transfer corresponding to emission of light. Yep.
Yes.
Stephen, would it make you comfortable if this explanation or formula for it will be there?
Well, I think that would only be improvements.
Okay. Yeah, thank you. Thank you for pointing everyone's attention on this, because there are several people who doing it every day and may have just forgotten to focus. Thank you. Good eye.
Oh, thank you.
Aaron, do you have any suggestions, constructive or destructive?
I don't know. It seems like my first impulse is would be only consider like maybe some of the panels, not all of them. I feel like Dimitri would disagree with that. Most of my comments on is just on aesthetics, and that's just something you kind of have to play with the format of the poster to see what looks best to remove the white space. And it's not easy, or it's not easy to fit like all this data very cleanly, but yeah, I think the one thing I would try is what Dimitri already said in the comments is to maybe try putting all the panels on the lower half. It might be a more natural fit.
Okay, yeah. Thank you, Aaron, for support.
Yeah, thank you.
Of this idea. Yeah, good. Are there any comments or questions from Yulun?
I guess maybe there are too many panels. Maybe just focus on high spin or use the low spin.
Okay.
And maybe you can add a table to summarize all other spin multiplicities.
Yeah, you mean just skip the intermediate spin multiplicity and keep the low and high, and then in that small table just mention the intermediate.
Yes. Okay.
It's also a good idea. Yeah, thank you. Yeah, it saves a lot of space for me as well.
Sarah, may I ask you to stop sharing for like a minute, and then you will come back? I want to show something.
Yeah, sure.
So, do you see your a version of your poster? Am I showing the right screen with the poster? Or
yes, you are.
Okay, yeah, thank you. So what I try to move, so the equations are moved to here. The conclusions are moved to here, and they can be swapped. And then there are three configurations, like low, middle, and high, and then they are spatially arranged. So maybe one can even add here the idea of David with diagrams, then showing the density of states, and then by arrows showing that it's like a map how to interpret the results. And then everything in this row will relate to dynamics of single electron hole, and everything in the lower row would correspond to the related to emission. So if this makes the poster too busy, and then maybe the middle panel here and there can be skipped, and then everything will be more sparse. But again, try to do creatively, because for those and let me stop sharing. You can return back to your version.
So overall, that looks, I think, better than mine. Thank you very much for editing my poster. Yeah, it looks nice.
And you'll do a couple of iterations more during the remaining months and see how it looks like. So those visitors who will read your abstract and will come with dedication to learn more about your work, they will read it anyway without independent on how it is arranged. But there will be people who will be just passing by with a glass of refreshment or piece of snack, and you'll stop by only if it catches their eye.
Mm-hmm.
And for those occasional visitors, the organization may help and promote your work to them.
Yep. Yeah.
Whew. Okay. There were a few more questions, or at least one more.
I think one you said, please consider the following option for spatial organization of the material. Intro methods does calculation at top side, 3 dynamical blocks at lower half of the poster. Yeah, you already mentioned that one.
And David, the very last comment, David suggests to state on the poster which figures go to which electronic configuration. But if we specially rearrange and connect by arrows, maybe it will do the work.
Yes, because yeah, I just mentioned it in the one sentence in the top. You can see here that there are for low, medial, and high spin multiplicities in terms of alpha and beta spin. Yeah, I just mentioned it like this. So they are in order. These are for the low, these are for the medial, and these are for the high.
There are people with different style of thinking, and this conference has a lot of famous, developed experts in the area who are in their retirement age, and they really think in words, sentences, and equations. They do not like figures. And your style of explaining it in a complete sentences would be appreciated. But there will be a lot of people of younger age group who prefer visual connections over text.
Yes, totally agree. Yeah.
Okay. Well, let's check if there are more questions to Sarah. More questions. One.
I have a question.
Yes, please.
Can you elaborate more on like how these results could be used for the applications that you mentioned?
The application, I think these clay minerals, the montmorillonite, I think they are good candidate in some pharmaceutical, biomaterial applications, because they are also good. They have some properties that are good for the catalysis, something like that. Yeah, I think. Yeah, this and actually the photoluminescence and the optical property of these materials studied very poorly. So I haven't found any paper actually that studied this optical and the photoluminescence property of this type of iron doped montmorillonite. So maybe we are the first people who studied this type of property. I'm not sure.
Thank you, London. Thank you, Sarah.
Yeah.
Okay, let's try this countdown once again. More questions, 1. More questions, 2. More questions, 2.5. More questions, 3. Let's thank Sarah once again.
Thank you very much.
Yeah, thank you. Kaya, are you here?
Yeah, I'm here.
Would you please share your poster? We will just glance together and maybe develop
Okay.
some suggestions.
Yeah. So this one, my poster, it's not good. Yeah. I have to change lots of things actually. So what's your suggestion?
So maybe just give a very brief guidance, like in which order should we look on figures or formulas?
Yeah.
Just general logic.
Me? Like
Yeah.
describe.
Yes, please explain how to look. Just teach us how in which order should we look on the elements of this poster.
So first I will explain the work, then the methodology section, and after that the result discussion part. And in the result discussion part there are few figures are here. I think it's not organized. I just put it in what I have a sequence in the paper. So maybe it will be good if you tell me that what in which way I need to be organized the poster. Then next week I will present. But here I think I just checked that I wrote the equation, non-adiabatic calculation, those equation 2 times here and this section also.
So assuming that visitors of the poster have attention disorder and cannot remember what they looked at a minute ago. Okay. Well, maybe one can use equations only once. But what is your main result? What is most interesting in your findings?
Oh my God, why it's look like that? This figure and this one. This two.
And so what is interesting? What should you look at?
Actually, okay. So from this figure, we are able to see that this yellow line refers the electrons, and it's relax faster than the blue line. That means the valence band, HOMO. So and from this figure, we are able to see that yellow line already condensed in the middle section, but the blue line still doesn't relax. It's so from the figure A and B, actually they are correlate, refers that electron relax faster than the holes. This one, and the second most important figure is this figure actually. So from the excitation energy figure, we are able to see that this peak C has the wide actually somewhere I didn't prepare. What's that So from this figure shows that a higher photoluminescence in peak C, and whether B and A shows the less photoluminescence. And if we look at the emission figure, we are able to see that peak A, B, C almost invisible. And but emission in the emissions spectrograph, there is a extra extra line. We are able to see that one in peak A. That one shows the higher emission, and that A, B, C, and M, that peak we are able to see from the intensity graph. So these two actually then most important result in this work, and I think, but it's not organized. So what's your solution, Professor?
No, we will accumulate questions.
Okay.
Generally, it looks really great. Let's just. So are you done guiding us through the poster, or you want to add any other important points that everyone should look at?
Because this one, I have one doubt. Like I was not able to fix those figures. This absorption figure and this one actually, if you remember that in the paper we use this one as a last figure number 7, but because of the space issues I put this one together. But if I need to explain the poster, then I have to like first I have to explain this, then and this one, then second is absorption, then third one is this figure, it goes in the left side, then fourth, fifth, and then this. So it's like I have to organize in that way. But yesterday I was not able to understand, so somehow just add. Now I need your suggestion.
Yeah, we will. There will be several questions, but I apologize for trying to ask my question first.
Okay.
But Kay, I'm really curious, and it's kind of set up question because I know the answer. But would you please explain the figure you started to focus our attention from? So in the middle, the one that you label as electron dash holes. Can you point your mouse on it?
Yes,
Lower, upper, a little upper, a little up. Yes, this one. And you are telling that electrons and holes condense to the center.
Yes.
Can you explain what it is and why it happens?
I think I know these things. I need to go back and say it's yellow line refers the electrons and the blue line refers the holes. So electron already condense in the middle section, Professor. And your question is why. So,
like which other figure on your poster would help us to interpret this observation?
I think this figure.
Which one?
This one. This non-adiabatic coupling.
Well, this non-adiabatic coupling explains dynamics in general for everything. But yes, but is there anything else? Like why, upon relaxation, both electrons and holes are condensed at the center of the polymer?
This one actually
Yes.
explained by this.
Exactly,
Like
exactly. Yes.
figure B.
Yes, I'm very happy. But can you? Is it clear for everyone, or maybe a little of explanation by K is needed?
I didn't explain. I will like the whole presentation. I will do that one next week.
But try explain it by 3 words right now.
Okay. So from this figure, just let's focus on the LUMO and HOMO. We are able to see that at the medial position, the orbit density of the orbital is maximum, whether at the edge of that LUMO, there is a density almost, we can say not zero, almost zero. So because of this, we are seeing the same thing in this figure. Like in the medial, the charge density is more, but at the edge it's less than the medial. But when it's LUMO plus 1, in LUMO plus 1, actually there is it's divided into 2 parts. So here it's a LUMO, but in there it's a LUMO plus 1. So in a LUMO plus 1, how to, okay. So there is divided into 2 parts, and there is 2 types of the so in the middle of that, it's a 0, and because it's divided into 2 parts, and there is almost 2 types of arc, like, and at the point here is 0, and the middle position there is a maximum, and at the edge it's almost 0. That orbital energy is density is 0. So the same things happen when we are seeing the electron holes in a non-adiabatic dynamics in a Z position. Here we are able to see that this relaxation electron here and this section is at the edge. We have some yellow line and blue line, but when it comes to that section in the middle, it's almost condensed. So that's the reason.
Okay, yeah, I'm very happy to hear it. Is everyone happy with this explanation? Let's play. I don't know if you had it the following game as kids: a broken telephone. When players sit next to each other and whisper message to the ear of the neighbor, and then pass it on, and then the very first and very last speak it out loud. And typically, part of a message is lost in transit. So, London, would you please explain as you understood the explanation of Kia?
Oh man, I don't know if I actually can.
Please try, and it will be a feedback if she will see what she explained well and what needs to be improved.
Well, I guess I don't know if I can try to really even explain like why the why the electrons kind of condense into the center, and I suppose the holes kind of do the same too. You were talking about how the orbitals basically go to zero density out at the edges, but I guess I don't know. I might have just missed why that happens.
It's pity that Aaron left because it was part of his thesis. But Kay, would you mind if London will try to explain your figure?
No, I will not.
Okay, so London, please focus on the first figure after the results and discussion.
Can you zoom in on that figure a little?
Okay. Is it okay?
Scroll up.
Just 1 minute.
Yes. So let's look only on the blue part, top part of this thing, that like LUMO +1, LUMO +2. What do you see, or what do you expect to see?
I guess I don't know what I would expect to see.
Come on. So the material that Kea is considering is conjugated polymer that is made of carbons, but due to specific bonds of the order 1.5, it conducts electricity same as metal.
Okay.
And we have strand of a limited length.
Say that again.
Strand of a limited length.
Okay.
It's like a stick with beginning and the end. So inside the electron can move freely, and outside it is forbidden.
Right. So I guess, I mean, if it's highly conductive, I suppose I would expect to see the LUMO, I guess, orbital to be more continuous, I guess, within the material rather than being kind of, these discrete blobs.
Well, there is some discrete nature where electrons like to be on atoms and do not like to be on a space between atoms or stuff like that. But let me bring a little figure, and maybe then you deliver the rest better than.
Well, it's blurred out.
Yeah. I'm using blur too much.
Can I enlarge your picture somehow? Seeing you inside it, look a potential well.
Okay. Yes. So inside your polymer, the energy is low. Outside it is high.
Yeah.
So it is particle in a
box.
Okay. Now, how do you interpret the blue orbitals?
Oh, are they just a bunch of little potential wells, I guess? Like
No.
What you're trying to...
The strand itself is a potential well.
Yeah.
And orbitals are just eigenstates of particle in a box.
Yeah.
So the lowest state has one big blob, and the second state has two big blobs.
Yeah.
Right?
Okay, yeah.
And if the system is in the LUMO +1 second state, then there is no density in the middle.
Right. Okay. Yeah.
And if you have transition from LUMO +1 to LUMO, then density condenses from these edges outside right to the center.
Would you be able to say that though, with states that are well above the ground state?
Well, if you go far, well, the pattern of particle in the box is repeated twice. Once for electrons above HOMO, and second for holes below band gap. So it's same like electrons and positrons, two sides from vacuum, and they repeat the same symmetry in semiconductors. Make sense?
Yeah, I guess so. I don't know.
Okay, is it close to what you were about to explain, or what you already explained? Okay. And let me attract attention of London. So the panel A, which shows like tilted, rotated DOS. So we have LUMO at -3, LUMO +1 at -2.5, and then LUMO +2 at -2 something. So the offset of levels increases.
Yeah.
Same as it is expected for particle in a box. So oligomers, limited length strengths of the conjugated polymers are quite popular examples of a particle in the box in real world. And K is very lucky to show this connection to the community. So it's like when K will be teaching quantum mechanics, it will be an ideal illustration for this chapter. Whew. Okay. Sorry for occupying everyone's attention. Let's look for the questions in the chat line. So the first question is from Amir.
Okay.
He is asking if the aspect ratio is consistent with the printable formats.
Like I use the width. He's asking about the format, the length and width.
Amir is asking about format.
It's kind of a square shape, maybe. I don't know. I just printed one poster here during my PhD. I think it's kind of more wide, those that we print here, but I don't know, maybe Dr. Kilin or others can comment.
So during the actual poster session, they will provide boards, and the size, the width will be limited. So you cannot do wider than whatever, 3.5 or 4 feet. But the height is unlimited. You can do it as tall as human height if you want to. But then visitors need to bow and read something on the level of foot which they may decline to do. So it's not forbidden. It's just hard to read something that is located at lower level. Next one is from David. Is there a reason you have separated your methods into 2 separate sections?
No reason, actually. When I did that, I have no space, but then this one is the second version, actually. I can add that one here. So there is no reason I didn't separate. Actually, there was no space before.
Next one by Amir. Reference section is a little large. There are some blank space in the method section.
Yeah, yes, I know.
That's personal taste. Maybe one can use smaller font for references, or Lolo is still here, or she left? Okay, it was question one to one. Then I think question for me. Why
I think you already answered those
Yes,
questions.
yes,
Right?
yes. We discussed it extensively.
Okay.
Next question for me: why electrons or holes transfer from one orbital to another? Like why electron jumps from LUMO +1 to LUMO?
I don't want to give a wrong answer, so
You can give a wrong answer. I authorize you.
because of the excitation, because we excite the system, that's the reason.
Okay, well, excitation promotes system to like LUMO +1, but why it returns to lower energy state? Why it relaxes?
It will be better, Professor, if you answer this.
But let's try. Everyone is welcome to contribute.
Because it wants to get relaxed and calm down and kind of go to the equilibrium state.
Yep, it's universal. Everything goes to equilibrium.
Maybe there is another reason. You are asking another thing, like what we wrote in the paper.
Well, the answer by Sarah is correct, but not detailed. So it answers why, but doesn't answer how. What's the
There are
mechanism?
several. Excuse me. There are several several level of energies actually. So one is the lowest one actually is the equilibrium, something like that. So the electron prefers to come back to the lowest level of the energy after excitation. So
good.
So that's also the emission and the excitation. After coming back from the highest level of the energy to the lowest one, it will emit this energy difference.
Maybe we can say like that. Maybe when we excite the system, after that it's relaxed. So that electron coupling are stronger than the holes. That's why it's happened.
Well, it's all. Everyone is correct, but there are some additional details in between. So Kea goes to very fine details for specific results of the system, and Sarah gave a little bit more details that let me translate her words. There is a universal law of energy conservation. So energy doesn't appear or disappear nowhere or from nowhere. So if a system jumps from higher level to lower level, the energy should be released into some other forms, either in form of light, in form of photons, or in form of heat, in form of nuclear vibrations. So if you have radiative process, then it is photoluminescence. If you have non-radiative, then energy is emitted in the form of oscillations of atoms. Right?
Okay.
And the mechanism how this release of energy happens, it is the figure that K is not showing right now, but what is on the right panel. Yeah, this
This?
non-adiabatic couplings. Yes. So since atoms are moving, the motion of atoms launches electronic couplings and leads to transitions between levels.
Hmm.
Yeah, I really like the discussion.
Hmm.
Thank you, Sarah. Thank you, Kea, for discussing it, and you are ready to answer this question in public when someone approaches your poster.
Need to actually I have to prepare for the poster. I didn't get time because today I had 2 classes and then again group meeting.
Yeah, do not worry. We have enough time, and you have your results ready. Some of us need to generate results in the time before the conference. David is asking, do the holes condense or it is just the electrons?
We already discussed that electron actually condense, not the hole.
And holes too, right?
Holes too, but later, like
later, but
after this. Yeah, both are condensed, but later. Electron condense first and then in holes. Like that's why I said like in our paper, this is the one of the most important things that electron. I also wrote that one in a conclusion. Electron relax faster than holes.
Okay. David, are you satisfied with the answer? Okay, good. Let me show quickly something. So this is what I was showing to London, right?
Yes,
and now I will show the same figure to David.
Okay.
Just in this way. So for the holes, the progression of particle in the box goes from downstairs. Okay, next one from David. Do you have the autocorrelation function on the poster for a specific reason? So below Redfield tensor, you show autocorrelation function, and David is asking, why are you showing it? Like, what do you want to teach us?
This one also related to non-adiabatic coupling. Actually, it's showing the same thing here in the middle. That one LUMO here, you can see that it relaxes here in the middle position. So actually, this figure correlate with the photoluminescence. That's why.
Okay, let me ask London to try answer this question. I know there was a discussion like 3 years ago between Eric Hobby and London on the conference in Boston about answer of this question, but I don't remember if it came to constructive conclusion. Okay, would you please show equations above this?
Yeah, sure.
Just scroll it here. And yeah, let's look on the second line, autocorrelation of NAC.
Yes. Yes.
So, question to London. What would you say, what do you remember about Fermi's golden rule? Or what is Fermi golden rule?
remember off the top of my head. If I see it already, oh here, I'll just Google it quick and maybe that'll spark
Right,
it.
right. That's smart. You didn't expect the group meeting will turn into exam.
Well, I mean, I kind of did. Oh yeah, it describes the transition rate. Okay. So it looks like the transition rate is usually not very time dependent. It's more so relevant, or the more important thing to look at, I guess, is the like overlap of the orbitals, I guess.
So Fermi's golden rule is that rate of transition is second power of interaction Hamiltonian, like interaction squared times density of states, right?
Yes, that seems reasonable.
It is probably what you saw by going into Wikipedia.
Something like that, yeah.
Right?
Yeah, yes. That
So
is on there.
Interaction squared times density of states. And this is quite simple equations that replacing a lot of our efforts and allows to interpret what is going on. The methodology that we try to use and to declare here is more advanced, but the figure that Kay is showing and that David is asking about is manifestation that in Fermi golden rule does work. So,
right, yes, because the autocorrelation function drops off basically immediately.
Yes. So although the theory instructs us to take this interaction matrix elements at time t and t plus tau at different time spots, we see that they are non-zero only if this time delay, if tau is 0 or very close to 0, which makes practical life much more simple. So it means we do not have memory, and based on this manifestation of Fermi's golden rule, our Redfield tensor is constant. It doesn't change over time. If the autocorrelation function would not drop instantaneously, this Redfield tensor would go up and down with time, and our calculations would take much longer. So we all are lucky guys.
Professor,
Yes?
maybe we can say that, if I'm wrong, then correct me, that these two figure we add here because this one shows the transition rate of the orbital.
Yes, correct. It shows mechanics, how we compute transition rates between orbitals. Yes.
Yes.
That's correct.
So I'm going to make a statement, and frankly, I agree with this statement, but the reason you've attached this is it shows that the rest of the calculation has worked properly.
Okay. That's also a good answer.
Yeah. Is there any novel reason or some reason besides the fact that it's showing that it's working correctly that you're including it? Or is it better to use that space for something that does give some interesting results, and we just assume that it worked correctly?
There is no theorem, there is no guarantee that Fermi's golden rule will work all the time.
True.
And especially for soft organic materials, there is a very high chance that it will not work. So it's just a good luck. But for small molecules with soft interatomic bonds, one may easily get oscillating autocorrelation functions, and the whole machinery may fail. So it is a proof. And the audience of Sunnybell conference is very appropriate to discuss these things or to show them. So they, most people there are not applied researchers, but more like methods developers, and they would appreciate it. David, make sense?
Yeah, I'm not disagreeing with it. I was just questioning it.
What I would add to make it even more spectacular on the aspect of methodology, I would add the noodles, the Spanish spaghetti, Italian spaghetti plot, the fluctuations of Kohn-Sham orbitals as function of time. So that show that HOMO and LUMO, as we go along molecular dynamics trajectory, they oscillate, and it is manifestations that Kohn-Sham orbitals change due to nuclear motion, and naturally orbital shapes change, and the couplings is non-zero. So it doesn't affect results, but it makes the procedure more clear. So if anyone has space, empty space, and doesn't know what to fit there as a decoration, I would put their spaghetti. And I'm confident that Yulun and Aaron are doing it on the daily basis, and maybe the script line to do this spaghetti plot was passed on to the rest of the attendees. It's not complicated. It's just like maybe 2 lines, very quick script. Okay, I'm talking too much. I think there are no more written questions. Let's try our countdown game.
There's you missed the first one from Stephen.
Okay.
Which is basically saying that in your Redfield tensor graph, it's a 3D graph, but you just have it side on, so you really can't see anything from it.
Okay, so Steven wants to tilt the image.
Yeah, basically.
Yeah, can be done. Okay. Yeah. Thank you, David, for bringing it to the attention. Okay, let's play countdown. More questions to KA1. More questions to KA2. More questions to KA3. Okay, please join me in thanking Kate.
And Professor, now tell me how to organize it in a correct way, the poster.
I think your organization is very reasonable. I would place this non-Redfield tensor and the autocorrelation function after orbitals and before dynamics, like either after orbitals or after spectra.
Okay.
So that it goes continuously, and you do not need, well, it's reasonable to have things in columns, but there are no prescriptions. No one will glorify or punish us if we do either vertical or horizontal. One can put panels in the horizontal arrangement, and sometimes it works better. So just do things creatively to communicate the message in the best way. But really good poster. I like it, and it is an interesting story.
Like first one I showed you this, like I sent you this version, then you comment, and after that I change it. Like,
yes, the second version is much better because it goes logically. The only thing that I would move non-adiabatic couplings before this electron hole dynamics.
Before this figure, right?
Right.
Okay. Okay, I will do that. And maybe when I will explain, like I saw today that I forgot to add the equation for this. Like, do I need to add the equation for this figure? this?
No, well, if you want, you can add anything, but I think it's already, at least no one was complaining and telling that something is missing.
Okay.
You may add equations for particle in the box, but only as a reference to point attention to. Most of the visitors will know this equation by memory, and
Okay. I think few comments you mentioned in the Google. Where are those comments? I think in a Google Drive. If I go to Google Drive, I will be able to see your comment.
oh, the only one
Where is
I
that?
asked for comments. Noodle
Yeah.
plot.
Yes, yes.
Second, in which order to show the figures, which you already addressed. Third one, what's the goal and main challenge? Just predict spectral signatures. And number four, other experimental data to compare with.
Okay, so here the thing is we compare the result, this one, like here just experimental data, and
For
that
absorption,
one
for absorption.
yes,
But
yes.
did you saw anything in the literature about emission?
No.
It's not mandatory. Just if something comes out to your attention, just be ready, because it is kind of natural question, like how good
Okay.
your predictions are. Okay. Yep.
Professor, you said that noodle plot. How to do that?
Just send a email maybe to Aaron and to Yulun and ask their suggestion.
Okay.
It is it's quite simple procedure. As soon as you have molecular dynamics, it just extracts energies of orbitals and then plots them into PostScript and PDF.
I'll do that.
Okay, very good. Yeah, many thanks to everyone for enthusiastic discussion. So if you were a presenter today, please consider to implement improvements. If you were not presenter, just consider to generate the first draft. And we will try to keep going and debug and improve posters as we approach the time of the conference. Did anyone arrange the book the airplane, or not yet?
The three of us that are in the office right now, I think, are doing that right after this.
Okay. Okay. And then whoever the first, maybe send an email to the rest of the group so that others can coordinate and either try to book similar flight, or if it is not possible, to think on arrangement different form of local transportation, so that those who arrive earlier do not wait too long. Amir, yes, are you all raising hand?
No, just I'm just confirming you.
Oh, okay. Yeah, well, very happy for this enthusiastic atmosphere, and I'm looking forward for continuation, and I think you will like the conference. Okay, meeting is dismissed. Anyone is welcome to disconnect. I'll stay here to answer any questions if needed. But if there are no questions, feel free to disconnect.
Yeah, just one thing, Dr. Bye, London. Just one thing, Dr. Is that please send me the poster that you made it for me and the grant information.
Okay, you'll do. And
that should be mentioned in the acknowledgement.
when you talk to Professor Shah, remind him that it would be, well, it's his decision, but it could be very reasonable to acknowledge the EPSCoR grant on clays. And then when he will be writing a report on this, on his contribution to this grant, he may mention your presentation, and he will be safe for the year.
Yes, sure. Okay, looking forward for that poster you modify for me and your grant number.
Okay.
Thank you very much. Have a great night. Bye, everybody. Bye, Dr. King.
Good night.
Dimitri.
Yes, David.
We are sitting in the office right now, and by we I mean me, Stephen, and Landon. So while we were sitting here during the group meeting, water started coming through the windows, just so you know.
I can move my webcam to show you.
Water coming through the windows? It's
Yes.
like swelling, or your breathing is condensing on the...
It's raining.
It's raining right inside?
Yeah.
Good. Very interesting. I think engineers would be happy to learn about it.
I've already talked to Dr. Rogers about it. He said to take pictures and send them, and he'll forward them to the company.
Is it raining outside? But there is no rain.
No,
but it's above freezing.
Okay, freeze.
It's raining inside.
Okay.
Damn, I bundled this cable so tight, I can't move it very far. One moment.
I also got that script we talked about yesterday working.
Okay, very good, very good. Thank you.
Do you have any advice, by the way, for fixing Python scripts? Because I've tried copying over Svetlana's old bin directory and it does not work.
Oh my God.
So, Steven, maybe you should do a couple of photographs with a cell phone and send it to me. And
I can't hear you, Professor.
Oh, yeah, you got that too.
Make photographs with a cell phone. You hear?
Try again.
Make photographs with your cell phone. Cell phone.
So I'll copy you on the email I'm going to send to Dr. Rogers about this.
Good.
A ladder?
Yeah.
No, I don't think so. And it's doing it in Dinesh's office as well. Much worse than mine, actually.
Okay. Steven, do you hear my microphone?
Hold on, I had to turn my volume up. I can hear you clearly now.
Okay. When you will be sending email about this complaint, maybe make photographs with a cell phone. So it will be not only words, but evidence.
Yes. Get more light since this room is actually fairly dark at night.
Yeah. There's no lights.
Right now, our plan is just complete the second manuscript, and how to did nurse working, or there is some problem still? I know
Nurse does work, but I have forgotten to announce it to